Hey, welcome to the Art of Code. My name is Martijn, and what you see behind me here is an effect that I did in the last video, a Truchet effect where we take two layers and weave them together. And because in the future I want to do more with 3D, with coordinate systems, with like deforming things and whatnot, I realized it would be cool to have a pattern to do that too, and then I thought, well, why not just make this thing that we made in 2D in 3D? So, if that interests you, stick around. Alright, so I have here a template that I'm going to start with, ray marching starting point. The link is down in the description. If you want to know exactly how this is made, I made a video specifically about that where I go everything completely from scratch, explain everything. But that's not what this video is about, and it will be too long otherwise, so that's why I'm starting here. Alright, so now the first thing I'm going to do is, let me just collapse some functions here that we're not looking at. We are looking at the getDist function here, so here I'm drawing a box that you see over here. The first thing that I want to do, because Truchet is an effect that works on a grid, well, the first thing that I want to do is I want to be able to visualize the grid so that it's a bit easier to figure out what we're doing. And for that, I'm going to go over here. I'm going to say float grid equals, and I'm going to first just make a ground plane. So the ground plane, the distance to the ground plane is just p dot y in my case. So let's boolean that in. So I say d equals the minimum of d and grid. So this is a Boolean union. I made a video about Booleans as well. Check out in the description. Alright, so now I have a plane and a box, and the plane cuts the box in half. But this is a one-sided plane. If I go underneath, it kind of starts glitching, the box disappears and whatnot. In order to make it double-sided, I'm going to put an absolute around here. And now you see that when I'm underneath, I can see the box, and when I'm above, I can see the box. I do have some glitches over here, and that's because my plane is infinitely thin. So let's give it some thickness, like that. So now I have a plane and a box. So now let's, in order to make the grid, what I'm going to do is I'm going to subtract that box from the plane. So instead of a Boolean union, I'm going to do a Boolean difference, which would be something like this. And then it subtracts there, so this is a Boolean difference. But obviously I don't want to, so what I figure is if I make a grid of boxes and I subtract the grid from this plane, then I can get a grid. Or if I have an array, an infinite array of boxes subtracted from the plane, I will get a grid. So I'm going to try to do that. So let's just look at the box by itself. Now, one thing is my grid is gonna have grid cells that are 1 by 1, and right now my box is 2 by 2 because this is the distance from the center. So I would have to do it like that to have a box that has 1 length on each dimension. But then it has to be even a little bit smaller than that because I need the lines of the grid to show. So let's just do 0.4. And now let's make a whole bunch of boxes. And the way to do that is I'm going to make a different coordinate. And oftentimes you want to kind of screw around with the coordinate to draw the particular object that you want to draw. Because you want to maybe repeat the coordinate, or you want to do some transformation, rotation, scale, what have you. But you still want to keep access to the original coordinate. So that for that reason, I often use a capital P that's my working coordinate, let's say. So if I put a capital P over here, then nothing changes because I haven't changed the coordinate yet. But what I can do now is I could repeat this coordinate. So one way to repeat a coordinate is to use a fract. And I'm going to repeat it in the XZ plane. So like the ground plane is XZ, up and down is Y. So I'm going to, in the XZ direction, I'm going to, instead of starting at 0 going to infinity, I'm going to use it throw it into a fract so that it goes from 0 to 1, and then 0 to 1 again, 0, like, so it keeps going 0, 1, 0, 1, 0, 1. So for that I'm going to do pxz, and now let's see what happens. So now we have a whole bunch of boxes for almost the price of one, which is pretty cool. It's just that we have some issue here because the origin of each box, so we're making a bunch of boxes, the origin of each box is in the corner right now, and because this box gets drawn at the origin, it gets drawn at the corner of each cell, and that's why you see it cut off. And so what I can do here is just subtract 0.5 from it, and then I have a whole bunch of boxes like that now I can subtract from the grid. So let me just do this in one go here. So let me say here grid equals the max of grid and minus the box, and so that's the Boolean difference, like that. And then I can say over here d equals grid. Okay, I have to declare it, float d equals grid, and now I have those boxes subtracted from the plane, which is pretty cool. And so now I can make this bigger to have a neat little grid. And you can see that in the distance here it gets a little bit noisy and dirty, and that's because you run out of ray marching steps. So I could just go over here, set that to, let's say, 300 to clean it up a lot more. All right, so that's my grid. That's pretty cool. So now inside of each grid, I'm going to draw a squiggle from the middle of all the edges to the middle of the other edge. So from here to here, I'm going to draw one, and from here to here, I'm going to draw one. And for those squiggles, they could be any kind of squiggle, but the simplest one that I could think of in 3D would be a quarter of a torus. And so let's do that. So I'm going to write out the distance function for a torus. I have a video specifically explaining how this works, so if you want to know why it is what it is, you can go to that video. Right now I'm just going to go through it quickly. So a torus has a small or a large radius and a small radius. And let me just write this out here. That would be the length of the vector 2 of the length of p dot. I'm going to have it flat on the ground, right? So it's in the xz direction minus the first radius, and then p dot y. Let's close my vector 2, close my length, and then subtract the thickness of the ring from that, which is R2. And let's see what that looks like. So let me say over here as the torus of P, and then so I want this well, eventually I want this torus to go from the middle of this edge to the middle of that edge, right? And so that's a radius, because the entire grid cell has a length of 1, right? A width and a height of 1. Well, then my radius, if it has to go from here to there, then my radius should be 0.5. So my big radius is 0.5, and my thickness could be whatever we want, but let's make it 10 times smaller. So yeah, so you don't have to put the 0 there. You could just do dot whatever. It's probably not compliant, but it's quicker, and I like it. All right, so let's see what that looks like. Let's put that together with the grid. So d equals min d and grid. All right, so that's all fine and dandy, but obviously I want it inside of each grid cell, so that's why I need to use my different coordinate that I made for that, so this coordinate. So let's see what that looks like. So now I have a bunch of tori in each grid cell, and now I just have to move that over, right? And in order to move that over, I can just take my xz coordinate and subtract from it. So if I subtract 0.1, 0.2, 0.3, you could see it will move into the corner over there. And so that is good, but then I also want it in the other corner, which would be minus over there. So now what I can do is I can draw two tori, one with 0.5 and one with minus 0.5, but there's a neater way to do it because I can just make a value s. I'll let me make that value. So s equals 1. So I can make a value s that evaluates to 1 when we're in the lower left quadrant, or in the lower left half of the cell, and it evaluates to minus 1 when we're in the top right of the cell. For that, we just have to kind of play around with the x and z coordinate a little bit. So if I compare the x and the z, I say, okay, well, let's say if the x is larger than the z, then evaluate to 1, otherwise evaluate to minus 1. Let's see what that looks like. Okay, so that gives me this. That's not what I want, so we just have to fudge this a little bit. So maybe minus over here. Yeah. Okay, so you just gotta fudge a little bit, see if it's maybe smaller than or larger than, or turn one of them around, say minus. So now I have two torus quadrants for the price of 1, which is pretty neat. All right, so now the last thing that I need in order to get a proper Truchet effect is to at random flip one of these tiles around, or flip some of these tiles around. And in order to flip a tile around, you just flip the coordinate system around. So I can say for the z, for instance, well, multiply that by minus 1 to flip it around. Okay. Same thing with the x. It doesn't matter if you have the x or if you flip it like this or you flip it like this. Doesn't really matter. But obviously, I don't want to flip it for all of the tiles. I want it to flip for some of the tiles. And for that, I'm going to make an ID value first. So let me go over here and say vec2 ID, which an ID value is a vector 2 that uniquely identifies each cell. That's just the floor of p.xz. So floor p.xz. And you got to be careful where you do that, right? Like you have to do that before you screw around with stuff. So if I put it over here, that's not going to work because I already kind of screwed with my pxz over here. So I have to do that over here. And now I have an ID value, and now I can use that unique ID value to turn it into a unique random value, like a number between 0 and 1. And then afterwards I can just say, well, if that number is larger than 0.5, then flip the tile, otherwise down. And so I need a hashing function. And yeah, let's put over here, float n equals hash21 of ID. And yeah, this is also called a hashing function, and that's 21 because it takes two numbers as an input, because this ID is a vector 2, right, as an x and a z, I suppose, and it gives me one random number as an output. And so I have to write that. Now there are 1,200 different ways to write a hashing function, and this is just one that I remembered. So there's other ways to do this. So it's going to take a vector 2 as an input, and then I'm going to say p equals the fractional component of p times some larger vector 2, and it really doesn't matter that much what these numbers are. So now that just took my 2D coordinate and multiplied it by a large number, and then it took the fractional component. So now on the x and on the y, I'm going to be somewhere between 0 and 1. And then I'm going to add the dot product of p and p plus some other number. And then I'm going to return the fractional component of p.x times p.y. So now don't ask me exactly what all of this is. This is just kind of screwing around with the number, cutting it up, folding it, and stuff like that, so that the final result looks like a random number, even though it's not really a random number. This is called a pseudo-random number. Pseudo-random number between 0 and 1. All right. So now we have that pseudo-random number, and now we can just say, well, if that number that is supposed to be between 0 and 1, if that's smaller than 0.5, which I'm not entirely sure what the exact distribution of these numbers is, but I believe it's fairly even. So So here you could say, well, if that number is smaller than 0.5, that would happen 50% of the time. Then flip a tile. So let's see what that does. And look at that. That makes a beautiful Truchet effect, because now some of the tiles are flipped, other tiles are not flipped, which is pretty cool. All right, so now what I'm going to do is I'm going to make this into a layer, because I'm going to have two layers and I'm going to weave them together. And so for that, I'm going to just copy this here, this get dist, put it over here. So that's my new get dist. And then over here, I'm just going to call this Truchet layer. And then over here, I can say float d equals Truchet layer of p, and then return that distance. And that shouldn't change anything. And it didn't. Because now the cool thing is that I can make multiple Truchet layers. So I can make Truchet layer 1, let's say, and Truchet layer 2. And now over here, I just get the union between those two, T1 and T2. All right, and that's still not going to change anything because both these Truchet layers are exactly at the same location. But now watch what happens if I remap the coordinate. So, and I want to shift it in the XZ because that's the ground plane, right? Not up and down. So I'm gonna shift it by half a tile. So 0 in the Y direction and then half a tile in the Z direction. And that needs to be a vector 3. And now we have two effects that are overlaid on top of each other. Let me just get rid of the grid real quick. That's pretty neat. But now I want them to be weaved together. All right, so in order to weave them, let me just look at one of them. So d equals T1, and let's turn the grid back on. Because what I want basically is I want, let's say the edges stay at 0, and then in the middle it either bobs up or bobs down. And if in the other layer it does exactly the opposite, then you can get a weave effect. So how do I do that? Well, first of all, let's see how do we move that torus. Well, the entire torus is not so hard because I could just go over here and remap this, my working coordinate, right, this p. I can say p dot y minus equals something, right? If I do that, then I can just move the entire torus up and down, right? I can also do a negative, and then it goes the other way. Obviously, I don't want to do that as a constant value. I want to do that based on where along the squiggle I am, right? Where along the arc I am. So let's say if we look at this square over here it doesn't move at all, and then over here it bobs up all the way to the top, and then it goes back down, let's say. So I need to know where along the torus I am in order to figure out how much up and down it needs to go. And if ever you need to know where along a perimeter you are, then you should always think about polar coordinates. I did a video specifically about polar coordinates. You can check it out in the link below. But for now, I'm just going to write it out. So I'm going to say float A equals a tan of p dot x and p dot z. So that gives me a polar coordinate from minus pi to pi. And then I'm going to use that to move my y up and down. And I'm going to throw that into a trig function. I'm going to throw it into a cosine just to see what that does. And well, it certainly moved stuff up and down. First of all, it's way too much, so let me just attenuate that by multiplying by a smaller than 1 number. And now, yeah, it moves up and down, and on some edges, you see on some edges it's at 0, but then on other edges it's not, right? And that's why you get these discontinuities. But that's fixed easy enough. I can just double my phase just to make it go up and down faster. Because basically right now it goes from, let's say, 0, and then on the other edge it's at maximum. But what we want is we want it to go from 0 to maximum back to 0 on the other edge, right? So what I can do here is I can just multiply that by 2. And now I have continuous squiggles. And yeah, so these are actually not 0 on the edges. They're actually 0 right in the middle. But it doesn't really matter. They, like, as long as the other, as it's well coordinated with the other layer, then it should be fine. At least this layer is continuous. There's no discontinuities, which is pretty cool. All right. So let's see what this looks like with 2 layers now. So I'll go over there. Let's get rid of the grid. And now we have 2 weaved layers. That's pretty neat. All right, so next I want it to be a little bit tighter, the way these are weaved together. And you could ask yourself, okay, how much does, because that's this number over here. And so you could ask yourself, how much should that be? Well, it's just the thickness of the torus. So the thickness of the torus is 0.05. So let's do that. 0.05. So now it's a little bit flatter. And now these squiggles should just be touching each other here and here. And now to make this more interesting, I thought to play with the shape of these squiggles because, let me just look at one again. So right now these are tori, right? So these are parts of a circle. But we can change that with a little trick here, because I can change. Let me see here. So this length function uses basically Pythagoras to figure out how long something is. And Pythagoras, if you remember, a squared plus b squared equals c squared. There's a squared in each of those, and so that's the normal Euclidean distance metric. But you can change the exponent there in order to get different distance metrics. And so for that, and that's called either Chebyshev or Minkowski distance. I got corrected the other day, or on my last video. I will put it on the screen so that you can Google it yourself. So basically, I'm going to have to write that function. So that's just a standard length, like think of Pythagoras, but instead of squared, we can use any exponent. And so for that. So I could just write Pythagoras something like this, right? I could say the power of p dot x, like p dot x squared, right? Plus power p dot y squared, and then the square root of that. And the square root, you can also write that as a power of 1 over 2, right? So that, not that, this. So that should be pretty much, that should be the same thing. And actually we can check that. So we could just say over here length, and then I just have to add a number here. And that didn't change anything because that's what this is, right? So now I could actually change it for k as well, because my k is already set to 2. So set this to k and 1 over k. And that still doesn't change anything because this is set to 2 over here. But now watch what happens if I change this to, let's say, 1.3. That's not supposed to happen. Okay, did I do something? Oh yeah, okay. Actually, there's one more thing here that you have to make sure of, is that these p dot x and p dot y, that they're positive, because on negative the pow sometimes doesn't work. So for that, I'm just going to do p equals the absolute of p. Okay, so now if I do 1.1, see, now I can make it more straight. I can make it more straight, or if I make it larger than 2, I can make it more square. So anywhere you're using a length, anywhere at all in whatever your distance function for a sphere or whatever, you can use this different metric to get different effects. So that's one thing that you can play around with. All right, so this k value, I'm just going to expose that. So I'm going to put that over here. I'm going to put that over here, float k. And now I have it inside of here, but I'm also going to expose it outside because I want to be able to change, have a different k value per Truchet layer. So I'm just going to also say over here, k and then over here, comma, float k. And now I have it over here. So now I can say over here 2 for this one, and for the other one I could say 1, let's say. And now let's put both of them together. And so now I have a straight one and a curved one together. Now you can see there's some glitches here, and that's because sometimes when you're screwing around with distance functions, they lose accuracy, and what you can get then is that you overstep in your ray marching, and so then you get these glitches. You can just make your steps smaller, and then usually you get rid of the glitches, though you have to be a little bit careful with that sometimes too, because your ray marching can get too slow, but I wouldn't worry too much about it at the moment. So let me just multiply that by 0.7, let's say, and you see that fixed a lot of issues here. And also let me make it a little bit thicker, so I can just subtract from that to make the straight one thicker. And right now the straight one is still kind of bobbing up and down in order to weave, and I don't want that to happen, so I'm going to, and that's this value over here, right? So I'm going to call that value wobble, and I'm going to expose that also. So float wobble. And then over here, my first one is going to wobble twice as much because the other one is not wobbling at all. So the other one I'm going to set to 0. And now we have it so that the straight one doesn't wobble and the other one does. And the other one goes neatly around it. Yeah, we could also do that different distance metric on the first length as well. So I could just do that. For now, I'm just going to have the same k value. You could have a different k value if you wanted to. So now that just makes it that the other one is straight. Although it does give me more glitches. So yeah, anyways, I'm not going to worry too much about the glitches. I'm just going to make this step size a tiny little bit smaller. So over here, I could multiply it by 0.9. So over here, let's see, there's a glitch. And let's see what happens if I do times 0.9. Okay, kind of fixed it. All right, that's great. So now let's add a little background to this real quick. Actually, let me just also make this one a little bit thicker. Yeah, something like that. That looks kind of cool. So let me add a little background as well. So I'm just going to add a layer underneath. So for that, well, if it's at the ground plane, then it would be this, right? But I'm just going to push it down a little bit. So plus 0.3. So now it's underneath. And now in order to get a little bit of separation between those two, I'm going to put some fake shadow on there. And in order to make a shadow, there's different ways, but like I'm going to use this Truchet distance again. And so now I could copy this and put this into my material section, but in programming it's never a good idea to have duplicate code because then you have data in two different areas and that can get out of sync and whatnot. So what I'm going to do is I'm going to cut this out here and I'm going to put that in its own function. So I'm going to do vec2 Truchet, takes as an input a 3D position, and as an output it gives me the distance to both of those layers. So now I can just return a vec2 with T1 and T2. Right, so now I don't, I have it only in one position. Vec2 T equals Truchet of P, and then over here instead of 1 and 2 I have to do dot x and dot y. That shouldn't change anything, and it doesn't, because now I can just call that same Truchet function over here, and I can say vec2 t equals Truchet, and that just gives me the distance to both of those, both of the Truchet squiggles. And so what I could do now here is I could say if t dot x is smaller than t dot y, then I know that I hit the squiggle and not the fence, let's say. So I could color it a different way. So I could do color times equals, let's say 1, 0.05, 0.05. You never want, in the colors, you never want want some color channel to be set to 0. It's always good to have a small, something small. Okay, yeah, so that's going to screw up with the ground, but for the ground we can do something else, because we can just say if the world coordinate is smaller than, let's say, -0.25, then I know that I hit the ground, right? So then I can do specific things for the ground, else I can do something else. So now I can have a separation in colors between the two. And now on the ground, I'm going to use this to make some sort of shadow. So I can use, let's say, the distance. I could just multiply it by the distance to, let's say, the x. And let's see what that looks like. Okay, so that's the distance to the red one. So that has some trouble because it doesn't take neighboring cells into account. So I'm just going to use the other one, because the other one's straight, and so it gives me nicer. It gives me a nicer effect, because you don't have issues between with boundaries and whatnot. And so I could just make that a little bit brighter if I wanted to. Whatever, I could just multiply that by 1.2, 1.5 even. Or fuck it, maybe even just 2. All right. Yeah, that's that. And then the last thing that I want to do maybe is, yeah, maybe I want to move this. So what I could do for that, well, again, so what I could do for that, I could say p.x plus equals I time, let's say, in order to make it move. But now it moves, but now the material side also needs to move, right, in order for that to be proper. So now I can do the same thing down here, but when it gets more complicated, then again I have the same code in 2 areas. So what I like to do is to make a transform function. So I can say p equals transform of p, and then that transform function does whatever transformation you want. So transform vec3 p, and then return p. Okay, so now I can do that inside of here. So I could have p.x plus equals I time. Okay, now that's gonna, why is there no overloaded function? Oh, there's an s missing here. Okay, so now I can just go over here, and I can do that transform again over here. So I can say p equals the transform of p, so that both of them are in sync. All right, so this is where I'm going to leave it for now. And then we have a beautiful pattern that we can use to maybe wrap around the cylinder, or wrap it around a torus, or wrap it around the sphere. That should be interesting. So yeah, so if that interests you, be sure to subscribe so that you don't miss it when I put out a new video. And yeah, in the meantime, thank you very much for watching, and I will see you next time.